Okay, not yet.
Yes. Is it possible to see the screen somehow?
No, I think I'm still stuck with just my face. I don't see the screen right now.
All right.
Otherwise, what I would do is you could just get started. I'll trust that the audience is able to see the screen, and I'll just go with my PowerPoint.
No, but there's still it's quite, because I have something to share here. So if you can,
Yeah.
I will again. I'll try to share my screen again. Okay.
Sure.
All right. Just I'll start the introduction. This. All right. All right. So good evening to everybody. Welcome to this tribology discussion. This session is sponsored by MOOHA, which is a digital assistant in tribology. It's one of the first automated laboratory information management system. And I will be the host. My name is Deepak. I'm the head of Ducom Digital and the head of global marketing for Ducom Instruments. A little bit of a quick update on what MOOHA is, because this connects us to the next step, another element that we cover, that is in smart industry. So this is a quick introduction to what MOOHA is. Basically, she brings a virtual tribology lab experience. This is the digital twin of our 4-ball tester, for example.
Hello. Hello. Yeah. You just dropped off for a minute.
Yeah.
Okay.
Can you see the screen now, Anand?
Not really. I can only see my screen. I can see only my face, but not the screen that you're sharing.
All right. So
I'll tell you what we'll do. I trust that the audience can see the screen, so I'll just ask you to scroll down the slides, and that should still work out.
Excellent. I will do that. So let me do some introduction to this, Anand. Right.
Sure.
So the guys, when you watch the video was related to how a combination of Internet of Things and augmented reality is able to create digital twin of tribometers, and that was delivered as a product by MOOHA. Moving forward to it, another important element in smart industry is additive manufacturing. What is additive manufacturing? It's a process of implementing manufacturing technology layer by layer, right? The benefits are that it helps reduce the cost of manufacturing, that the value will be to the customer, so he can expect to have a high value at low price. And the most important element to the industry, which is adopting additive manufacturing, is they are able to be competitive to any changes in the market trend, right? So that's the power. So it creates that mass customization, it creates that mass modularization, it creates that mass variety of it, right? as a result of it, you see the benefits here. 3D printing, additive manufacturing, which used to be largely limited to a prototype tool, is moving towards the mainstream as a manufacturing tool. It has changed how we design, how we manufacture, and how we sell products. As an example here from the PricewaterhouseCoopers survey, the growth in these additive manufactured products, is going to reach 9.59 billion when it comes to those products being, consumed by aerospace industry, and the products consumed, products that are being manufactured by using the additive manufacturing technology, consumed in medical technology sector, will reach 5.59 billion in 2030, and the additive manufacturing products in our automotive sector would reach to 2.61 billion. There are orders of magnitude difference, if you see a growth, if you see 15 years from 2015 to 2030. To discuss this, in depth about how additive manufacturing would be playing a very important role in various sectors, and how tribology would be creating more value here, and what are those concepts of where one has to be aware of before jumping into additive manufacturing. We have Dr. K. Anand, who has more than 20 years of expertise, in tribology. It's very close. He started out, I guess, when I read his PhD work a little bit. He worked extensively in erosion. It's very nice of it, and where additive manufacturing is kind of playing an important role there. So he is a consultant GE Power. He is a chief manager of IIT Madras and Deakin University together. And the topic of his talk will be additive manufacturing and tribology applications. So we welcome Dr. Anand here. And Anand, shall I share the screen with your slides?
Sure. Sure. So if you could, again, gentlemen, I would really like to thank you for attending the meeting. And I would like to thank Dr. Deepak and Ducom for having invited me over. A talk like this to a global audience gives me the chance to actually, take stock of what's been the journey so far, and where do we need to go, and how do we actually make things happen, where we combine the functionality of the additive manufacturing along with essentially meeting the requirements of component surfaces to take care of wear. So it's quite an opportunity, and it's quite a challenge. And I want to first talk about this subject from the perspective of what does it take to solve a wear problem. And so that's the place I want to start. Take you through the different forms of wear, what could be the kind of solutions that are being used today, and then start looking at additive manufacturing, see where is the convergence, and see whether there is any scope for additive manufacturing and materials that we have discovered for wear resistance, how can they combine together? But more importantly, how do we take the unique capabilities of additive manufacturing in transcending the problem? So I'll come to that too. So that's really what this talk is going to be about. And without too much of ado, what I really want to do is go to slide number 3. So I'd like to request Dr. Deepak to scroll down to slide number 3, if you may.
I'm there, Anand. Go ahead.
Sure. Right. So my apologies for a fairly busy slide, but essentially where we are is that the wear in itself is a multifaceted problem, and depending on what the operating conditions are, you can essentially have wear taking place through multiple modes and multiple mechanisms. I think we need to kind of understand both the aspects. So as we know, wear essentially is loss of material from a component surface. You can lose it physically. You can lose it because something melted because of frictional heat. We can lose it primarily because something happened in combination with mechanical forces and chemical agents. So you could have both corrosion and wear taking place at the same time. Sometimes you can have both oxidation and wear taking place at the same time. So that's the right-hand side of the fairly busy sketch I have. And so now if you scroll down and start looking at mechanical wear, it breaks into adhesive wear, abrasive wear, fatigue wear, and then the chemical part breaks into corrosive wear. And all of these take place through a whole bunch of modes and mechanisms. So you have sliding wear leading to adhesive wear, threading wear contributing to adhesive wear, impact wear can be both adhesive and some form of abrasion depending on the hardness of the surfaces. And then you have threading wear, which is reciprocatory motion, slidey wear, which becomes solid particle erosion. It's a fairly busy mode, and you'll get to see more of this in the next slide, where the modes are essentially explained in a more simple manner. The graph that you see on the top right is a very interesting graph. What we have essentially is a specific wear rate, where the wear rate is actually normalized to operating conditions, typically the sliding distance and the applied load. And you actually see that the leftmost point is 10 to the power of minus 16, and the rightmost point is 10 to the power of minus 2. And
Anand,
yeah.
I'm sorry to intervene. I'm on the slide number 4.
You should be on slide number 3. I'm sorry.
My apologies. Go ahead.
Yeah. Right. So the point I really wanted to make was that you can essentially have an order of 16 difference, 10 to the power of 16 difference in wear rate, depending on what mode you are operating. So the wonderful zone that you would like to be in is a hydrodynamic lubrication. That's a Toyota car, where you can essentially start the car, run it for 400,000 miles, and you still find that it's good. And the folklore is that if you start taking a look at the amount of wear that is taking place in the cylinder piston ring, it's in the range of 15, 20, 25 microns. So the wear is so infinitesimally small when you have a lubrication working really well and working in tandem with the component surfaces. Then when the lubricants essentially break down, you start getting into boundary lubrication, and the wear shoots up by a factor of million. And then when you get into no lubrication and just plain and simple adhesive wear shoots up by under 1,000 to 2,000, 10,000. And when you have abrasion thrown in, where something is much harder than the other surface, wear shoots up by under a factor of 10. So you can have this huge change in wear, starting from almost negligible to very severe. And you want to keep that in mind, because if you want to see additive manufacturing solve these kind of problems, you need to start mapping out what the solution space should be in your head. And the graph on the bottom right, which shows abrasion, erosion, impact, gulling, and sliding. And it kind of tells you what is the difference in terms of wear through these different mechanisms. When you're looking at lubricated sliding, it's in the range of 10 microns. When you're looking at impact, it can be as much as 20 millimeters or 20,000 microns. When you're looking at, very heavy duty abrasion, which is the green graph on the right, you can actually lose 2 to 3 inches of material, which is around 50,000 microns of material. So having said that, what are the different modes of wear? We would go to slide 4. It's a simple cartoon that tells you what are the different modes of wear. You have adhesive wear, typically takes place when the component hardness of the two surfaces are roughly the same. So that's H1 of the surface number 1, H2 of surface number 2. Those are the hardness values. They're roughly the same. With the abrasive wear, one of the surfaces becomes much harder than the other. And quite often, it also happens because you have sharp particles thrown in, which is what you see here. Sharp angular particles, which are hard. Those are the ones that actually cause abrasion. Now you take the same sharp angular particle and throw it into a water slurry or throw it into an airstream and let it go and impact. You have solid particle erosion, which is what is shown. Fatigue wear, I'll skip it for now. Corrosive wear. Threading wear becomes a very important one because that's something that actually bites us quite a bit in the industry all across. So you have two contacting surfaces undergoing motion in two opposite directions. So they're kind of going back and forth against each other, and that leads to a form of damage which is quite severe. You can either have threading fatigue or threading wear, but I won't get into those nuances. Then on the top right, you actually see two circles, and you see these red objects which are essentially blades on these circles. And this represents a cartoon of what a turbo machinery does. The blades are rotating mounted on the rotor. They're rotating concentrically with respect to the casing, except that it's not always concentric. There can be an ovality in the casing for different reasons. The rotational orbit, it may itself go out of whack and you can have a rub taking place. And this takes place at a velocity of Mach 1 or more. And this kind of wear is also quite significant and severe. And then on the bottom right, we have droplet erosion and cavitation erosion, which is because of either air bubbles in liquid or just plain and simple water droplets coming and hitting the sample. So these are all the different modes of wear. So when you have wear, the first trick is, can you actually stop the wear from taking place altogether by stopping the motion? So when you have, let's say, two surfaces in contact, bolted together, tighten the bolt and make sure that the bolts never unfasten, completely bolted together tight, and eliminate vibratory excitations, nothing is going to wear. So that's what you do when you arrest relative motion. The other way of looking at it, and this kind of leads into additive, eliminate contacting parts in an assembly so that you don't have all these little components rubbing against each other, vibrating against each other, undergoing relative motion in the first place. So how do you eliminate contacting parts and still make this assembly work? That's the trick that additive manufacturers actually dream about. And that's something that all of us want to do. I mean, get rid of this confluence of design and materials in such a way that you simplify the design, remove the number of components, and in that process, you would have actually reduced the probability of wear. The third bullet is reduce contact forces. So the one old trick as far as wear is concerned, and there would always be exceptions, but very generally, the wear increases linearly with contact stress. Higher the contact stress, greater the wear. So can you do something about reducing contact stress? And how do you do that when the aero forces are still the same? Again, there we start looking into additive because you can start building in compliance structures that would essentially reduce the spring constant of the assembly. And so for the same displacement, you don't have the same kind of forces acting on the component surfaces, and it can actually remove or reduce wear substantially. Create better surfaces. And that's really what I've done for a living over the last 30 years. Create component surfaces with better and better materials that actually have better resistance to wear. And the question that I'm posing now, and the question that I'll pose towards the end as well, is how do you essentially combine additive manufacturing with better wear resistance? Now I'm going to jump gears a little bit, show some cartoons of turbo machinery. This goes back to the ASM handbook in 1992 by J. Shell, Aircraft Engines. He was my mentor. And I do want to say that he passed away many years ago. But he was essentially a master in this field, and he knew everything about wear in turbo machinery. This is a very busy slide, but what I really want to say is that all these black dots that you see represent what is called as sliding and threading wear. And then this open circles represent high-speed rubbing, which takes place in Mach 1 velocity. Then you have these bearings, which are high-speed, highly loaded bearings. Really sorry about the small font. And then you have fasteners, which can undergo threading. In a very simple snapshot, this covers the entire spectrum of the kind of wear that you would take place. And what you would also see is that the engine is rotating. It's on the wing. It's taking off from the runway. You can have sand and snow and salt during winter, and it could pick up all the sand into the engine, which would cause erosion. You could have flights going back and forth between Bombay and the Middle East, for example. Bombay is dry and dusty for 8 months in a year. It's very wet for 4 months in a year, but it goes into the Middle East, and what it picks up again is sand, and you have solid particle erosion taking place, which is very severe. So you have solid particle erosion, you have high-speed rub, you have threading, and you have lubricated sliding with bearings. That's aircraft engines for you. And the temperatures range all the way from room temperature in the front of the engine to around 650 degrees Celsius midway at the compressor exhaust, and then to around 1100 degrees Celsius on the high pressure turbine section, which again decays down to maybe around 700 C as you exit the engine. So why does it matter? I'll ignore the line on pitting corrosion. It's a different mechanism. But when I look at threading and impact, we can see 3 to 5x reduction in life. Looking at solid particle erosion, there can be a 3x reduction in life. There can be a 1 to 2% drop in efficiency. Look at high-speed rub, you have 1 to 2% drop in efficiency. And then you have high temperature thermal barrier, which I would leave for now. But what happens is that you have a wide range of operating conditions, as the table shows, all the way from 10 MPa stress to 1000 MPa stress, room temperature to 1000 degrees Celsius for threading and impact. What would be the solution for threading and impact? We have a complete suite of coatings, and I would really recommend that you look at ASM Handbook Volume 18, 1992, and also look at ASM Handbook Volume 18, 2017. I was asked to write a review article for wear and erosion issues on gas and steam turbines. And so between aviation and gas and steam turbines, the entire aspect of tribology essentially gets discussed in these chapters. But you can really have soft coatings. And these soft coatings essentially help in redistributing stresses. Along with the soft coating, you throw in a dry film lubricant. And this lubricant essentially reduces friction, reduces high running and wear, keeps the overall wear rates fairly low because the lubricant in tandem with the soft coating works really well together to manage life and wear in aircraft engines. And you would see often similar strategies coming into play in some of the turbo machinery with steam turbines and gas turbines, especially the use of dry film lubricants. Solid particle erosion, we use PVD coatings and thermal sprayed carbide coatings. Clearance control, we have soft abradable coatings. And as far as high temperature is concerned, we use thermal barrier coatings. Now, not all of you will be working in the turbo machinery area. So if I start taking a look at dry sliding wear, lubricated wear, abrasive wear, solid particle erosion, and cavitation in all the other industries, it's extensive. I don't know how many of you are remember the days of 1980s, if you're in the US, or if you're in India in the 1970s and 80s. The cars we had essentially had very thick paint, and the exterior was not glossy. It had a very dull matte finish. The reason why it had a matte finish is because when you cold roll the steel, the wear on the rolls essentially marks the wear on the marks on the steel, and you essentially have the steel coming out of the cold rolling mill with a matte finish because of wear. It would have scratches, it would have a matte finish, and so on and so forth. But if you start looking at the vehicles that are produced all the way from the early 90s through now, every car that you buy essentially has got a bright, beautiful, glossy finish. And that's because the cold roll steel goes through all these rollers at a speed of around 35 to 50 meters per second, goes to rollers and gets annealed at maybe 850 to 1000 degrees Celsius. But you really have protective coatings on all the roll surfaces to ensure that the steel strip essentially has a bright surface finish. Maybe all aesthetic, but are there other reasons why you want to worry about sliding wear? Metallic seals, for example, these are used in pumps and compressors to keep hazardous gases at bay, allow them and ensure that they stay where they need to, or essentially have pumps and compressors work without oil so that there are no oil fumes, so that these oil fumes don't get into the pharma industry reactors and essentially contaminate the medicines that you buy. So if you don't want oil floating around in a pharmaceutical plant, you need to have pumps that can work without oil. And some of those essentially use metallic seals, and those metallic seals work brilliantly under sliding and impact conditions, primarily because of the materials that are used. Very simple example of dry sliding wear. You're driving a car, you want to brake to essentially stop at a stoplight. And that happens because you have brake pads that work against brake drums ad infinitum for maybe 20 to 30,000 miles quite often. And that's phenomenal to see the kind of durability that some of these brake pads have. I don't want to essentially go through this line by line, but what you would actually get a drift of as you see this table is that there are a whole bunch of mechanisms. And for each of these mechanisms, we have examples of could be the kind of wear that would take place. And we have examples of what the solutions are for these. And when you start taking a look at these solutions, I talked about carbide coatings, I talked about PVD for the piston rings, talked about DLC for the piston rings, talked about apatite coatings for orthopedic implants, talked about white cast irons. So these are all a combination of materials and processes, and they have been optimized for decades to actually get it to work for these applications. And the wear is actually very severe. It's not, it's not a light form of damage. The subsurface damage is very intense. And these materials and processes, as they come together, essentially provide you the solution. So the question then is, how do you kind of go on the additive manufacturing route and still come up with a solution? So that's what I'll come to in the subsequent slides. One more example of wear, but a good example of wear. Without wear, you cannot have machine surfaces. All the machine shops would go dead if you didn't have wear taking place. And it's a very complicated phenomenon. You have a cutting tool, gets in contact with the workpiece. It digs into the workpiece, causes intense plastic deformation and shear. And as the intense plastic deformation takes place in a very localized region, the heat builds up and the surfaces oxidize and they slide against the cutting tool, leading to essentially what we call as crater wear. Underneath the cutting tool, in the wake, you have tensile stresses. You can have abrasion taking place. You can have chipping taking place. And if you see this graph right here, you can actually see 3 different wear mechanisms taking place on the cutting tool when you do the machining. So what are the solutions? We have tool steels for easy work pieces. You shift to carbides when you start getting into heavier loads, higher cutting speeds. You switch to CBN and diamond when you're essentially working against other materials. So CBN essentially works with aluminum. And then To reduce the wear, you actually have PVD and CVD coatings on the cutting tools. So it's a combination of the bulk material plus the coating plus a selection of the bulk material for specific work pieces that actually make all of this work. So again, what you want to say is that the wear is a surface phenomenon, and the bulk materials essentially perform the function of providing strength, durability, reliability, and so on. And when the surface and the bulk is actually married together to have a durable component, you do that through surface engineering. And that's really what I want to talk to you about. I'm going to skip slides right now, and I'm going to go to where the graph is that shows engineering tungsten carbide based thermal spray coatings for fretting resistance. I'm not sure whether you're able to get to that, Deepak.
What would be the slide number, Anand, for that? I have tungsten carbide at cobalt, 6%, right? And then
keep scrolling down.
Yeah.
If you'll actually see essentially a slide that says powder feedstock.
Yeah,
10
I am
to
on
35.
that.
Yeah, perfect. Yeah. So some of the best materials that you have today to resist wear, even now after 30 years, is tungsten carbide cobalt. We use it for cutting tools. It's used in mining industry. It's used in aviation parts to protect components from wear. It gets used in pumps. It gets used in compressors. It's really extensive to see where it gets used. But the trick is two things. One is that I want to have a coating which is dense. So I don't want a porous coating which has got pore integrity, because the pores essentially are crack formers. The pores would then come together and they would form a crack, and the crack would propagate. And irrespective of how good your material was, because it is deposited in a manner of poor integrity, the whole thing would come apart. So, sorry. Yeah. So what you do essentially is coat these materials. You start off with powders which are around 10 to 35 microns, and you put them through a thermal spray gun. And I got plasma. It's a high temperature process with moderate velocity, 200 meters per second. And then I have high velocity oxyfuel, which is lower in temperature, but higher in velocity. And you have other variants, D-gun, super D-gun, HEF, which get to even higher velocities. And the HEF gets into lower temperatures. The D-gun gets into higher temperatures. But this combination of kinetic energy and temperature really produces a coating with tremendous integrity. And depending on the temperature that the parts saw, you can either have parts with all the carbides retained, or you can have coatings with quite a bit of the carbides dissolved into the binder. And that essentially gives you coatings with different properties. So that's what you're going to see in the next slide, which is engineering tungsten carbide-based thermal spray coatings for fretting resistance. Fretting resistance, among other things, is a function of fracture toughness. I can't show you all the data I have on fretting wear properties. That gets into stuff which is proprietary. But what you can see is that for the same composition, by adjusting the process parameters and the equipment used, I can essentially have a fracture toughness change by an order of magnitude of 3. So I can go from a fracture toughness of around 2.5 MPa square root meter to around 8 MPa square root meter. And that's really because of the kind of microstructures that these coating processes have produced. The reason why I wanted to cover this is that it is just not the material that actually makes it work. It's the combination of the material and process that actually makes this entire wear process work. So when you're beginning to look at additive manufacturing, you can't just say, hey, I'll somehow switch the powders and go to something which is of higher resistance using a DMLD process. You really have to start looking at how do you tailor the properties of the surface to get you where you need to be. So that's what I want to leave you with. And in this whole world of surface engineering, and I'm kind of going to go back and connect this to the table that we had before that showed different wear modes for different industries with different coating processes. We can essentially do two things. One is take a component surface and go underneath and change the structure and composition, which is what we do through ion implantation, through carbidizing, through nitriding, and induction hardening. Or I can take a component and essentially deposit stuff on the surface. And that's what I would do, essentially going from hard facing, thermal spray, plating, CVD, PVD. I think there is some formatting error, but yeah, broadly, the hard facing can get you an inch of material on the surface. Thermal spray can get you about 2 to 3 millimeters, about a tenth. But typically, when you're looking at a carbide coating, you're looking at 250 microns, which is around 10 mils. The PVD ends up at around 30 to 40 microns max, 2 to 3 microns typical. The CVD ends up at around 10 to 20 microns typical. The plating is 50 to 100 microns typical. So you do a lot of things at that length scale to essentially change the component surface. Right. So I'm going to get to, lead into essentially additive manufacturing here. Any questions so far?
Anand, they are posting questions. I guess if you finish up, then we have all the questions together, and we will have a discussion with you on that.
Perfect. Yeah. Perfect.
Go ahead.
So how do you marry the world of wear solutions and additive manufacturing? So if you move to the next slide, which says, can additive manufacturing reduce wear? The first thing you want to do essentially is see whether you can arrest relative motion. And I'll give you some examples of that, at least one example of that. So when you have a component assembly, let's say a casing, a liner, a hook, all coming together, then you really have sliding interfaces between the casing, the liner, and the hook. But if you actually were able to combine all of these into one single part, you really wouldn't have anything which actually moves around. There are no nuts, there are no bolts to get loosened. This is one single component. And apart from doing many things, such as reducing design complexity, reducing weight, easing up the supply chain, you could potentially eliminate some of the wear issues that would typically take place in turbo machinery because of all these moving parts. Second one essentially is, as I said to you before, when the contact stress is high, the wear is high. When the contact stress is low, the wear is low. There may be exceptions here and there, but this is a rule. This is largely true. If I had a component loaded to, let's say, 1 KSI, and I had another set of components loaded at 10 KSI, and the materials are the same, you're going to find out that at 10 KSI, the wear is much higher. May not be 10 times higher, but definitely much higher. So if you had something under your belt, which you would use to essentially reduce the component load by making stuff more compliant, you would be able to reduce wear. But apart from that, the reason why stuff essentially wears is because there is a relative motion. And the reason why you have relative motion is because the vibratory excitation modes have not been dampened. You've not eliminated vibratory excitation modes. And if they do vibrate, you have not been able to dampen them. So can you do something with the component design that could essentially dampen out the vibrations and also eliminate some of the vibratory excitation modes? And of course, what I've done for the past 25 years or 30 years is essentially try to create better surfaces, test better surfaces, and see how will they perform. So I want to start giving you some examples of those. So here is an example of a brake pad assembly So you actually have the pad and you have the calipers, you have actuators, and they all come together. And ultimately, when you press the brake pedal, there's something in the system that actually pushes the brake pad against the brake drum and causes the vehicle to slow down or stop. Um, Certainly, you need at least a couple of moving surfaces. You cannot eliminate motion altogether. But could you essentially take a look at this kind of an assembly and say, how do you bring in the functionality of a braking actuation system, reduce the number of components that are involved, and use additive manufacturing along the way to essentially make this whole design simpler? Because while you do so, what you've done essentially is reduce the number of moving parts and therefore reduce the kind of wear that will take place. Um, what you also have to remember is the brake pad essentially does not just go on its own and contact the brake drum. It's guided. So when you have wear taking place and the wear is not uniform, you don't have the brake pad going, smack on normal to the surface perfectly. There can be a little bit of misorientation here and there. And therefore, when you have a little bit of misorientation here and there, the brake pad doesn't jam smoothly and uniformly against the surface. It's kind of cocked in some angle, which will lead to higher stresses and therefore much higher wear. So there are a lot that can be gained through designs which are brought to bear through additive manufacturing, where you could actually control the forces. And when you control the forces, you actually reduce wear. If you go to the additive manufacturing literature, it's replete with examples of designs where you could still have the same functionality, but because the component is not one rigid body, but essentially it's a web of interlinking meshes where the mode of loading is controlled, the bending loads are controlled, the flexure loads are controlled. This kind of a system is both lightweight, has got great properties in terms of being compliant, has got great properties in terms of dampening out vibrations. So if you had a component which is still rectangular in shape, but underneath, inside, there's a scaffold which is compliant, you could actually make this component actually contact, with not the same kind of contact forces, and there could be substantial amount of dampening that could take place because of how the component got designed in the first place. So these are some examples of essentially how you could reduce contact stresses. You could reduce sliding distance because it doesn't vibrate anymore or vibrate to the same extent anymore. And all of that actually works out really, really well. So stuff to think about. I'm not saying that we can jump and go and get this done, but you really have to go and take a look at these kind of concepts and still see whether that design feature has got the manufacturing integrity. Does it have the overall reliability in terms of the overall balance of properties for such a design to work? But there are more and more examples of concepts like these getting used in additive to actually solve problems. Finally, come to creating better surfaces. Each wear mode and each industry segment has a material solution for which the combination of the material and the process used is essentially a gold standard. So I'm just reading out examples. Gear shifter forks, they use moly. Transmission gears could be induction hardened or carburized. Compressor airfoils, depending on the application, could be PVD or coated or thermal spray coated. Jaw crushers could have hard facing on them. Orthopedic implants could have chromite. So when I give you these examples, these are examples of specific materials applied by specific processes to ensure that both the material and the process come together the component surface to take care of the wear problem. In this context, the question to ask is, can I still get additive manufacturing to have these kind of surfaces with this form of functionality? And I don't want to be a rosy, cheeked optimist, but I really want to kind of um, you know, understand what the challenges are and see how do we use the strength of additive and the strength of materials and the strength of processes to come together to make this happen. So let's go to the next slide, which gets into um, keeping all of this in view, which is that we already had gold standards. So you want to kind of kick off the gold standards and still be additive and still be better. So where would you use them? And I think this is really where the discussion would be very rich and very useful. I would think of valve seats. That's my personal opinion. Primarily because they're small, primarily because it's a great opportunity to grade the composition, make it more resistant towards the surface, and essentially more tough underneath. Bearing cages, extremely complicated in shapes. Right now, we don't use the best materials that are available because the processing in itself is a challenge. So what can you do with bearing cages? It can actually work really well. Take a look at bevel gears. They're very complicated in shape. The bite-to-fly ratio is very poor. What can you do with additive manufacturing of moderately sized bevel gears? They could actually work well. Machine tools, non-contact seals, implants. So what's the criteria for us to say, I want to do it by additive, and I think I have a better way problem. I mean, I have a better way solution. So the criteria could be any of these graded compositions, which are performance and cost driven. So an example of cost driven is that I have a die which is used for forging. I could really have, medium carbon steel as the die material for the bulk of it. And as I come to the top, an inch and a half or two, where the temperature goes up, the contact forces go up, I could actually start shifting to die steels and so on and so forth. I didn't really have to make that entire die out of, let's say, an expensive tool steel. If I could do all of this through additive, then I really have an approach which takes care of both performance and cost. Complex shapes, bevel gear is a good example. Textured surfaces, I want to have dimpled surfaces in which I can keep lubricants in. So when I have surfaces sliding against each other, these dimples release lubricant, and that lubricant essentially reduces wear, keeps the friction low. So a lot of examples, but two things. One is that there needs to be a technical need, there needs to be an economic need, and the solutions that you think of need to be materials that are printable. Can't go to materials which are not printable. I get to repair applications. I think this is a very sweet spot. Um, and we used to dream of this, back in even the late 90s, mid 90s. India was struggling at that point in time to be cost competitive. Imports just got allowed. Suddenly, production volumes began to go up because everything expanded in scale at that time period. Cars, scooters, motorbikes, appliances, the whole 9 yards. So there were a lot of stuff which is actually getting forged. There were a lot of stuff which is getting cast. And when you saw local damage, you literally had to either machine off the damage and rebuild. And once you get to a thickness which is less than what's allowed, you would really have to, throw away the die. You would have to throw away something which is around $15,000 to $20,000 in cost, and that would break the backs of the small scale industries because they would spend so much of money in just tools to make things work. So if you could actually get additive to work in a scenario like this, where you do some scanning, you get to understand what the desired size and shape was of this particular part, you get to understand what is the current size and shape of the part, and essentially have a CAD drawing that tells you what needs to be printed on the part, where, to what thickness. You could actually report, restore the part, and this could be a really vital cog in the circular economy. And I would say, this is a great opportunity to go and look at additive and see how do you get it to work. A very contrarian view to essentially some of the cool stuff that we would think about, but this is really, brick and mortar. This is really where, money gets wasted. we essentially have a carbon dioxide footprint because we throw away stuff back into the furnace and use them when you could actually be reusing them. So when you start taking a look at some of these parts, some of these aspects, what are the additive manufacturing processes which are relevant? So that's the AM process selection slide. When you think of additive, we think of lasers. We think of lasers going, scanning back and forth, building parts, very complex in shape and so on and so forth. That's a very important piece of the puzzle, but that's really good for small, complex parts with demanding properties, where dimensional precision is of greatest importance. But then when I have larger parts which need local buildup, I could really look at DMLD as a process. And when you have larger parts where the project properties are not so exacting, I could be looking at binder jets, which gets me a printed part with a density of around 95%. There's a 5% porosity. Those kind of features, lend themselves beautifully to, let's say, lubricant impregnation. So when you're looking at journal bearings, could you actually bind a jet that kind of a component composition, impregnate lubricant, and bond it against essentially a backing plate and roll it and get it to be a journal bearing. And then when you start beginning to look at the world of dies for forging and so on, where the dies are huge, could be half a room for an automotive component. We now have in IIT Deakin, for example, examples of numerically controlled weld overlay machines. So they've done stuff to the weld overlay head where the bead itself is much finer in diameter, maybe around maybe around a millimeter or millimeter and a half. The heat input is actually controlled much more carefully. So you have stuff like cold metal transfer going on. But the entire deposition head is put on a numerically controlled machine. So you could actually lay out the part that needs to be printed. And instead of it being printed through a laser, it gets printed by a weld overlay machine, which is a lot cheaper. And of course, a lot more heat and so on and so forth. But when you're looking at examples where 95% of the build essentially doesn't have to be precise, this kind of a mechanism essentially is very good. Forgot to talk about cold spray. That's an important mechanism as well. It's an offshoot of thermal spraying, except that you don't melt the parts. The powders are shot at room temperature, not at room temperature, let's say 400 to 500 degrees Celsius. 400 to 500 degrees Celsius, and at a velocity of around 1,000 meters per second, and that works brilliantly. So, what are the challenges from a wear perspective? Going back to additive and the whole aspect of solving wear. We have current workhorses, and I talked about that. So, need to benchmark additive manufacturing capable materials against what's been successful in resisting wear in different modes. And I would really start with stuff like stellite. I would start with, let's say, tool steels. I would start with, white cast irons. I will not go to high volume fraction tungsten carbide cobalt to be additively manufactured. I think that would be much harder. But when you start beginning to look at metallic materials, which are workhorses for wear resistance under many conditions, those kind of stuff, those kind of materials is really what I would look at for additive manufacturing to solve specific issues. While thermal spray coatings and PVD are additive processes, you don't subtract, you only add. We're not being completely honest with ourselves when you look at the spirit of additive. The spirit of additive is that you want to produce a component of net shape, very complex in shape, very complex in functionality, which blends in bulk properties and surface properties seamlessly. And so you want to start looking at stuff like stellite as the kind of materials that you would use for additive manufacturing to solve many problems. Maybe, as I said, cast irons, maybe do binder jetting and lubricant impregnation. Many things are possible. Ultimately, when you start looking at additive manufacturing, where the real opportunity may well lie in using the design flexibility additive manufacturing brings to manage wear, so that I can reduce contact stresses, I can reduce vibratory excitation, I can have surfaces which are more, I can have components which are more compliant. So that's really where I would leave you with. And this is a photograph of IIT Madras, which I took a few months ago before COVID. It's a campus inside a forest with maybe around 1,000 spotted deer and 300 black bucks, plenty of snakes. But this gives us the right environment to actually think and innovate and think in a sustainable manner. Thank you.
Thank you very much, Anand. A lot of snakes and a lot of black bucks. It's quite a contrasting combination.
Yeah.
Something you like, sometimes you run away from. I think that's also what fascinates additive manufacturing. People who are intrigued about the potential of additive manufacturing, I'm quite sure they learned quite a lot from your talk today, right? So I would look for some questions that I have here with me, and I guess you can start answering them. So there's a question from Mr. Amit Kudva from Plasmatron in Mumbai. So he has two questions, and the first question is about how can the carbide powder injection into the HVOF gas stream be optimized to improve coating quality?
That's. I'm very sorry.
No problem. No problem. Yeah.
I think it's got to do with the gun design to start with, and what kind of equipment you have, and I think I know the kind of equipment that Mr. Kudva has is really good, state of the art JP 5000 and JP 8000, and maybe that's the place you really want to start with, but start exploring some of the other processes. But I would really say, other HVO processes like the MedTech gun. What I would really say, in the overall scheme of things, the way that kind of gun is designed, and the way the process is controlled, that would remain as one of the best devices to look at for a lot of the engineering applications. Of course, there are niche applications where you want the velocities to back down a little bit to control component distortion. Maybe you want the flame temperatures to go up a bit to take care of some of the feedstock that you want to spray, and you begin to look at some of the guns that use propylene or hydrogen as a fuel more closely. But the JP 5000, 8000 really gets you there, and really, it's really a question of running DOEs with the specific powders that you get with the gun and the process parameters to see as to how they could be optimized to get you the properties that you want and to get you the kind of deposition efficiency you need, so that you kind of meet the process economics.
Nice. The guys who are watching this, if you can post your comment on the chat box and the YouTube, right? The next question is from Dr. Krzysztof Zizek from Łódź University of Technology in Poland. The question is, how can additive manufacturing be used when it comes to incorporating solid lubricants in materials of components in tribological pairs, whatever? So, do you have any practical examples where the products are there available with solid lubricants into materials for tribology pairs?
Yeah. See, I would give you two answers. The first answer is binder jet, because for additive processes that you would think of, this process essentially inherently has a certain level of porosity because the binder is burnt out. And if the parts get sintered after that, you still end up with a component with this with a net percentage porosity in the range of 5%. And these pores are fairly big, they're not small. I mean, when I say big, I'm not saying a millimeter, but let's say 5-10 microns, and that's more than enough to actually entrain lubricants, greases, for example, or even solid lubricating particles. So binder jet is actually one place that I would go to. The other area which has not been explored well, and unfortunately it's a thermal spray answer, and I would hate to call thermal spray strictly as additive manufacturing, because you really don't have the kind of control in controlling component sizes and shapes. What you know is that this is a device that can get you a thickness of maybe 50 microns to 200 to 2500 microns with a precision of 50 microns or so. And that's really not enough to say it's additive. But having said that, we don't see enough work being done in combining hard particles with lubricating additives. There are a few examples, but not enough. And maybe that's an area that we need to work on a little bit more.
Nice. Anand, I have a question. Meanwhile, a bit curious on how the small scale industry, let's say small businesses, make use of additive manufacturing to become more competitive and kind of challenge the big shots, let's say, in industry. Because what we have understood a little bit, let's take example of GE itself. They have, in Pune, they have built, the manufacturer, they relies largely on 3D printers, and their approach is pan-industrial manufacturing, where you can create operational synergies across the company. So what it means across different divisions. So what it means is, if there is one manufacturing facility that manufactures the parts for the turbines, when the business is going down for the turbine, then they can start manufacturing. So use the same facility for, let's say, manufacturing wind turbine blades for renewable energy, right? So you create the pan idea when you have additive manufacturing. How can something like this be very useful for small businesses?
Right. The first thing I want to say is that without saying anything which is proprietary, when you take a look at the world of turbo machinery, the honest answer is that 95% to 98% of the components that are assembled in an engine are made through conventional ways. There may be a few select parts which are made additively, because it's only additive that can get you the ability to manufacture these complex shapes, which the conventional processes cannot. So let's say that 95% of what you see in turbo machinery is made through conventional technologies. But having said that, the answer goes back to essentially the small scale industries. What's really good about the additive processes, including the DMLS, is that they don't necessarily cost the moon. For about a little over $1 million, maybe $2 to $3 million, you can get additive machines that are actually functional and can do a whole bunch of shapes and sizes and so on. And then when you have the laser-based machines and you have the binder jet machines, which are significantly cheaper, you can start using these to do prototyping. Prototyping to show what a component would look like. Prototyping to make patterns for casting, for example, which very significantly reduce the waiting time to get some of these things made, including costs. So a lot of uses for additive in the world of small scale industries, provided you can find somebody who actually has a machine around you. And what I'm beginning to find is that there are many such people, even in India, who actually have 3D printers which do metallic 3D printing, backed by pretty knowledgeable people who are quite world-class in what they can provide you. So we need to see more and more of these people come up and essentially fulfill the need for speed, the need for prototyping, the need to enable manufacturing through patterns and so on and so forth to actually get this done. Are they actually going to manufacture 95% of the world's parts? The answer is probably no. But 95% of the world's parts are still going to be made additively. And I always give this example to people. Take a look at a motorbike in India. It's got this, it's an air-cooled engine. The radiator fins are extremely complicated. And you would wonder as to how is it actually made. It's made through die casting.
Right.
And India manufactures something to the tune of 15 to 20 million vehicles per year.
Right.
So you have 50 to 20 million parts which are getting knocked out through die casting, very intricate in shape. And in each of these parts just takes 2 minutes to cast, literally. Whereas additive machine would have been at it for maybe around 3 to 4 days. So until some of those challenges are actually solved, additive is not going to replace every component that you would see out there, but it's a very, very important enabler in that it brings in design flexibility. It helps you prototype. It enables manufacturing very, very well.
Nice, nice. There's a question from Professor Shrikant Joshi from University West in Sweden.
Sure.
Hard particles with lubricating additives, aren't these much more easily done by thermal spray and direct metal deposition than powder bed fusion approaches?
Very simple, no doubts. Yeah. It's good to see Shrikant, and I mean, he's got some very cool processes, and I think those are at the cutting edge for sure.
Okay. My other question, Anand, is role of digitalization, right? So Industry 4.0, basically under the umbrella of smart industry, we say that additive manufacturing is only next to artificial intelligence and Internet of Things and so on and so forth. How do you see that digital transformation in the field of tribology when you talk about additive manufacturing, when you talk about Internet of Things and artificial intelligence, how all of these digital tools would enable tribology better to serve problems, let's say to lower wear, improve wear resistance, lower friction, and so on and so forth. So what is your understanding of that?
Sure. There are 2-3 aspects to this whole thing. Unfortunately, both the practitioners in wear and the end users of components that see wear reduces problem to improving life. But if you would see on the slides that I showed you, the difference between a 1960s Ambassador car and a 2010 Honda Accord was actually the cold rolling mill and managing wear between the rolls and the steel strip. You would never get a Honda Accord to look what it does unless the tribology of rolling was actually managed. So where does digitalization actually fit in all of this? We talked about efficiency too. When component surfaces become rough because of erosion, you set up eddies on the component surface that easily knock off 3 to 4% of efficiency. And this 3 to 4% of efficiency loss in a steam turbine, I was just doing the math. You take the surface degradation in thermal power plants in the country, that's about 290 million tons of carbon dioxide saved, about 8% of the emissions that India has. Staggering, actually. So the thing is, how do you actually quantify these things? Can I actually measure the steam turbine efficiency and nail it down to, hey, I lost clearance here. I essentially had erosion here. I had surface eddies here. It's possible if you actually collect data and you really have the analytics to back you up to figure out what is causing what. And if you're able to do that, you're actually able to actually build the value story of what, where, and tribology actually does for you in real life. So that's efficiency loss in turbo machinery. You take an example of trucks. Many of these trucks, essentially, when they accelerate, you see this huge tons of black smoke coming out. Why is that the case? The cylinder liner essentially is plateau honed. It's got these little wedges or grooves in which the oil is retained. You accelerate, you dump a whole bunch of fuel, the RPM increases, the piston ring scrapes the sides of the cylinder liner and throws the oil into the combustion cavity. The oil is not designed for combustion, it's designed for lubrication. So when it burns, it generates a whole bunch of carbon, and all the carbon comes out as black smoke, and the emissions go up. So what do you have by way of sensors, the Internet of Things, to kind of say, hey, you know what, your cylinder liner is actually degrading pretty badly, and you really need something better than what you got today.
Right.
Right. So you could really build in a lot of diagnostics if you really had the data and the intelligence to understand what this data means, and tie this diagnostics down to degradation phenomenon. If it's wear, it's wear. If it's something else, it's something else. But the collecting the data and tying it to mechanisms of degradation will ultimately point to a surface which is worn.
Right.
So it builds the value story.
Yeah, actually, it's a good example, Anand. So, for example, if you have connected devices, right? So for example, let's take the example, the trucks, and then somehow you're able to monitor the change in temperature, or even for that case, if you look at the percentage of iron content or something in your lubricant, you get an idea of condition monitoring of your engine. Right, you have an idea of the quality of engine components when they are sliding. So if that could be, directly relayed, live, to have some information about when the wear happened, what time and what sort of actions have to be taken immediately after that. And let's say in the case that you realize that this truck is somewhere in Chennai, and then it has to change its components. Right, it has to change the ring.
Yeah.
The guy would have to, in a conventional way, he has to go to a very specific garage, or let's say a very specific place, to get his components repaired or replaced. Right, for that.
Yeah.
But in the case of additive manufacturing, the beauty of it is if you have connected 3D printers worldwide, right? You can actually, at the location in Chennai, before it ends into catastrophic wear or damage, in Chennai, he can basically manufacture and get those components replaced through, because of the benefits of 3D printer being there, right?
Yeah. So, in principle, you could 3D print piston rings.
Yeah.
In principle, you could 3D print diesel engine exhaust filters.
Right.
In principle, you could 3D print gear shifter forks. These are very common examples where you have a breakdown because the gears don't engage,
right.
And often it's the gear shifter fork. In principle, you would know when the brake drums are going to give up. When the axle is going to give up. That may not be additive, but IoT. But yeah, if you take additive and IoT and see a solution, it could be a piston ring, it could be diesel engine filters, it could be valve seats, it could be gear shifter forks. You already really got 4 or 5 components.
Yeah.
And I think if you do a little bit more of digging up, you're going to find a lot more.
Yeah, so there are benefits of connected devices,
Yeah.
and that's basically, and additive manufacturing helps us in terms of replacement of those parts at any point, at any place in the world, I guess, in a way. We have a question from Abhishek Srivatsava. So can we print self-lubricating bearings by additive manufacturing, say SLM or DED?
Yeah, so when you start taking a look at self-lubricating, you're looking at graphite, you're looking at graphene, you're looking at molybdenum disulfide, tungsten disulfide, hexagonal boron nitride. These would be the lubricants. Or you just say, I want a porous bedding. And in that porous bedding, in the pores, I'm going to vacuum impregnate the lubricant. That's probably the more easier part. So if you had a bedding, yeah, multiple ways to make porous beddings, but a laser-based additive method would be an expensive one. Maybe a binder jet would be a somewhat cheaper one, but to do the self-lubricating really well, you probably need about 20 to 30% volume fraction of pores. At least the additive manufacturing processes, the way I understand them, probably don't get you to that kind of a porosity. But having said that, if your bedding is well designed and you still have enough of volume fraction of lubricants that work well, you could, in principle, do additive manufacturing of self-lubricating beddings. So you got to actually select the process carefully and make sure that it actually works for you.
Nice. We will take one more question and one last topic for discussion, Anand, before, and I know it's too late. Thank you very much for being here so far. The question is from Professor Bikramjit Basu from Indian Institute of Science. So he would like to know more about DED-based processes and how that could be used to reduce wear, with the focus on with the extensive focus on biological implant wear, if you have an idea.
Yeah. I actually seen some talks coming out of IIT Madras. I'm sure Dr. Basu, you know, Dr. Saravana Kumar, Engineering Design Lab. At least the concepts they're talking about are really fascinating. So you go and get yourself scanned. There is a design library that says your ortho joints have to look like this, but due to wear, it's actually, you undergone loss of dimensions in quite a few specific locations on your bones, and you know that you really need to get an implant done. So the implant essentially remembers what should be the expected size of your bone based on the scans that have been done, and you press the button, it gets printed, and you essentially have an ortho implant which is made of the right metal, maybe titanium. Maybe it's got the right surface, and you probably have to cheat a little bit. Maybe go to the PVD chamber and get maybe a chrome nitride done to essentially improve wear and improve self-lubrication. Maybe put a DLC done with a PECVD. But in principle, all of this could be done because you have a scanner, you have a design library, you get to understand what your current size is, you get to understand what the build needs to be, and you go and get the thing custom built and tailor the surface and put it in. And that whole thing would work out really well. I'm not sure as to whether I answered your question completely. I think there are elements that are still missing in my answer. So you have this titanium implant, for example. It is still not tissue friendly. You probably need an apatite coating of some sorts that's got a composition which is similar to the human bone, which should be the right receptacle for tissues to get back in and grow. And you would have to start looking at that aspect as well. I'm not sure as to whether I answered your question completely or not.
I guess he will stay in touch with you to have more interaction.
Sure.
I think on this.
Sure.
Yeah. I think the wear mechanisms for of the components or parts manufactured by additive manufacturing and through additive manufacturing and the conventional tools and dies process, I think that there's no is there an extensive study that connects the mechanisms are similar between the conventional and the additive manufactured parts, or how different are they?
This is my
in
opinion.
General.
I think, the surface mechanisms are going to be the same. So ultimately, when you start taking a look at the wear process, it's because you have two parts in relative motion. They set up a stress field which is maybe around 150, 200 microns deep at the maximum. And everything takes place in the 200 to 250 micron space on both sides of the components. The additive process essentially is a bulk process. And the properties of the bulk don't necessarily have a bearing on what happens on the top 100, 200 microns. Quite often is less than that.
Right.
And what's also very important, and I didn't quite cover that, is that the surface deformation mechanisms, that are a precursor to the wear event actually taking place, material getting lost. The surface deformation mechanisms are very intense and very severe. The strains could be 1000%. The strain rates could be 10 to the power of 4. Local temperature rise could be very significant. And nothing that the part would have actually seen in its day-to-day testing would have prepared the surface for that. And that's part of the reason why we get into surface engineering. And many of us are so passionate around that. So when you want to tailor wear resistance to the surface of a component, if you had a way to grade the powder composition in such a way that they start off at where you need to be, let's say steel, and then you come close to the surface, and through this DED process, for example, or DMLD process, for example, you change the powder feeder and essentially switch to, let's say, a stellite, switch to a tribology.
Right.
Then you actually start building in the functionality that you want, where the bulk is made of something else and the surface is made of something else. And it doesn't have to be two separate operations. You would get everything kind of met at the same time. The component geometry, the component functionality, the surface properties, etc. But then if you're getting into a wear mode which is so severe, the stellites don't cut it anymore, and you have to go to some of the tungsten carbides, you have to go to the chrome carbides. I don't think additive is going to help you. So it's really around being in that spot where metals actually work to solve a wear problem.
Right. Nice. Anand, we are coming to the last part of this discussion, and this is something, the question I often engage with a lot of speakers on this platform, and largely to the point that it will inspire the several tribologists in the world who are starting out their career in tribology, or who wants to take up tribology as their career. The question is, what role did tribology play in your career? How much of it you owe to tribology? Because this is interesting. You had experience. You have industrial experience. You spent quite a lot of time in General Electrics and then power, and then now you are the chief manager of the kind of how do you call this? IIT Madras and Deakin University. A cluster. Is that correct to say, Anand? Or is
a center of excellence?
Yeah, center of excellence. Sorry. So you have the center of, so you're chief manager of it. So you have seen the side of the industry. You're looking at now into how academicians, how the academy or institutions work. And a center of excellence is also in industry. Center of excellence is also in academia. There are differences.
Yeah,
I guess. In any of these, tribology has been the common theme, I guess.
Yeah.
Right. So can you elaborate a little bit on how it has helped you in your career?
Right. I think I'm one of the few who has been married to a field and I stayed true to it
married to
for 40 years.
40 years.
I mean, 39 years to be precise. My journey in tribology started with my BE project, where I did work on wear of aluminum corundum composites. And then I went from sliding wear to friction materials to solid particle erosion, and then to coatings, and then coatings for multiple applications, and so on and so forth. That journey is stuff that some of the people who know me actually know that I've been in this field. What is the career lesson for me? It is that you stay in a field for some time and you actually develop ways to connect to it, which are very deep and very instinctive and very intuitive. When people ask you questions, the answers come off flying pretty effortlessly because of the fact that you spend so much of time in the field. You can't be a genius, you have to spend time in the field. That's when you actually pick up that kind of a knowledge. What's the second thing which is very unique about tribology is that, as I said, the wear conditions are very severe. and there's nothing in the bulk material they could have prepared it for what happens on the surface. Strain rates of 10 to the power of 3, we test at strain rates of 10 to the power of minus 2. Strains of 300%, 1000%, we test to a percentage elongation to failure of 35 to 40% max for most of the materials. So what is it in the material that actually made it survive those conditions of strain and strain rate? It's still not completely understood.
No.
I think some of the people that we work with have tried to crack it, but I don't think people have completely understood it from the perspective of parameters, blah, 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 blah. So what it comes to is that it's such a unique phenomenon that you got to start respecting what happens on the surface, pay attention to it, let the data teach you, and let the materials teach you. Preconceived notions don't necessarily work. And that essentially has become an approach to life for me.
Right. Oh, nice. Because tribology, I completely, tribology is something you learn, by experience rather than from having it fed through books. So
actually, what happens is that experience kind of teaches you what works,
right?
And then you start building hypotheses on why it works. And once you have this combination of data, what works, and the hypothesis, and then you're given a new scenario, you're actually able to visualize what the solution space would be like. And what you try to do is stay with maybe a solution space which is kind of tried and tested, 70 to 80% of it. But you really want to do the 20 to 30%, which is new in every program that you work on. If you're somehow able to swing it, finding the money to do it and so on and so forth, you actually find that you could actually invent many things along the way, and you learn along the way.
Right. And Anand, is there so in your new, if I got a new position as a chief manager of this consortium or the Center of Excellence there, how would tribology benefit from that Center of Excellence? Can you be quick, briefly highlight a little bit so that those who would look?
So there are some. I think all of you should get in touch with two people. Dr. B.S. Murthy, who's the director of IIT Hyderabad, and the other is Dr. Dan Fabijanik, who basically works in the Institute of Frontier Materials at Deakin University. And through a challenge that we posed to them while I was in GE, we've been working on some new class of materials, high entropy alloys, for example. And some of them are actually showing some very interesting properties, both in terms of bulk mechanical behavior and also in terms of tribological properties. I don't know whether we fully understand why they performed well, but some of the materials that we've looked at are really there in terms of weight capabilities. And that's one mechanism by which you can actually use an ecosystem like this to develop new materials for tribology. But my role with this IIT Deakin is more than tribology. It is about connecting materials to major pillars that are needed in the industry: lightweighting, functional materials, sustainable manufacture for a circular economy. And I alluded to that in some of these slides right here. Those are the three pillars that we're working on. And some of the cross-cutting technologies that actually work, include computational materials engineering. And we are right now running a seminar on that too.
Nice. All right. Good luck with that, Anand, and thank you very much for your time today. I know you had a very busy schedule, and despite that, you made some time to share your insights on additive manufacturing. And I'm quite sure that a lot of us who tuned in to out of either curiosity or having the burning problems at the moment, looking for solutions through additive manufacturing, we have gained a lot after your talk. I appreciate it. Thank you very much.
Yeah, I just want to leave the audience with one thought, which is that there are no, single great, brilliant experts in the field. All of us are, and it's what we make out to be. Number one, and number two is that we actually sharpen our thinking only when we challenge each other and only when we debate. And push each other to a higher technical level. And we don't do enough of that, but I think if you start doing this, we make each of us a better person and more successful in our careers. Even when I'm past retirement and full of gray hair, I think there are still problems to crack. I really appreciate this, Deepak. I really enjoyed talking to all of you, and thank you very much for your time.
Thank you very much, Anand. So for those who have tuned in, we will have the next series of Tribology discussions would begin in the month of September. First week, we have a few interesting talks lined up in that month, and you will all, I know, whoever have subscribed onto our YouTube channel, you'll get an update about that schedule in the coming days. Thank you for everyone, and for those questions whom we were not able to take up in this session. I'm quite sure I will send those questions to Dr. Anand, and then I will connect you, the person who asked the questions with Dr. Anand to prepare a rebuttal. It's a very short question, some of them, and I'm quite sure Anand will be quite happy to get connected and discuss that with you. He's passionate about tribology. Yeah. All right. Thank you. Take care. Bye.
Thank you. Thank you.